Hello everyone, we're back to talk about probability some more. And in homework problem number 14, we're given a wave function for a particle confined to a 1D box of length L. And this wave function is basically the same wave function we've been working with all chapter. And we're given a bunch of different lengths or a bunch of different boundaries within this 10 nanometer long box that we're going to see how probable is it to find the particle within that bound. So our goal here is to find the probability that a particle exists in different length bounds. All right, and for our equations, really it's just the probability equation. Which we know as P equals, integrate, the bounds will vary depending on what we're given, psi squared dx. Some other things that are just nice to have, we know the length is 10 nanometer, and we are assuming that this wave function is already normalized because this factor on the outside is very familiar at this point. So we can just write our assumption, because it doesn't say in the problem that it's normalized, but we're going to assume psi is normalized. So we don't have to do another normalization to this. We're going to assume it's already done. So we're going to take our probability equation. P equals, integrate. I'm going to write L1 and L2 because in all of these subparts A through E, we're given different values of L. So I'm going to just write L1 to L2 so we can get an algebraic expression for the solution. And then in the end, we can just plug in all of the values and make it so we don't have to do the same steps over and over. So integrate L1 to L2, psi squared of dx, plug in psi squared. We get P equals, integrate from L1 to L2, root 2 over L, sine pi x over L squared dx. Doing every step. P equals from L1 to L2. Oh, I could have taken that out. Well, I'll just leave it in for now and take it out next time. Sine squared pi x over L dx. And remember, we can't actually integrate sine squared, so we have to use that trig identity. Okay, there's enough room. Sine squared x equals 1 minus cosine 2x over 2. So we can substitute this back into the integral. So coming over here, we have P equals 2 over L, integrate L1 to L2, 1 minus cosine 2 pi x over L over 2 dx. And then from here, we can actually integrate. So integrating this, we get, we can pull the 1/2 out, so the 2 cancels, and we wind up with just 1 over L. So we get P equals 1 over L. Integral of 1 is just x, minus, then the integral of cosine of 2 pi x over L is L over 2 pi sine 2 pi x over L from L1 to L2. Okay, now plugging in these values, L2 first, we get equals 1 over L, big bracket, L2 minus L over 2 pi sine 2 pi L2 over L minus the same thing, but with L1 instead. And then what I'm going to do is I'm going to group the like terms together. So I'm going to just put these little L's together and then the signs together and factor out this L over 2 pi term. So we get P equals 1 over L times all of this minus L over 2 pi times sine 2 pi L2 over L minus sine 2 pi L1 over, yes, L1 over L. Ooh, just squeezed it in. Okay. And then we can distribute the 1 over L to everything, and then we'll get our probability equation that will make doing the rest a lot easier. So we have L2 minus L1 over L minus 1 over 2 pi sine 2 pi L2 over L minus sine 2 pi L1 over L. Okay, now that we have this nice equation that lets us just plug and chug, we can do that. Okay, on to the next page. I've rewritten this equation at the top, so you can have it for reference, and I'm not going to write it out plugged and chugged every single time because it's going to take up a lot of room and take too much of your time, and I don't want to do that. So using this equation, we can go to the first part, part A, and we're given L1 and L2 as 4.95 nanometer and 5.05 nanometer. So just plugging this in, we should get P equals about, I'll do a little squiggle, 0.02. So about 2% of the time, the particle exists, oops, in this boundary. Okay, for part B, we're given L1 equals 1.95 nanometer and L2 equals 2.05 nanometer. And for this, after you plug and chug, you should get a value of 0.007. So 0.7% of the time, you're going to find the particle within this boundary. And it's a bit smaller. If you think about it, it makes sense because it's not in the center. And we can think about all of these answers. Let me draw a particle in a box. If we're assuming n equals 1, I mean, we are because the n is removed. Really, there's an n in this wave function, but they basically made it so that n equals 1 because we can't see it. It's as if all of this stuff is multiplied by 1. So for n equals 1, we know that the wave function is going to look like this. Okay? And here's 0 nanometer, and then 10 nanometer. So if we think this bound is just right in the middle of that peak, within 0.1 distance, and that's 2% of the time, which makes sense because over the grand scheme of things, we really expect it to be there right in the middle on average. And then here on the outside, around 2 nanometer, that probability is a lot lower. Continuing with this, for part C, we have L1 equals 9.90 nanometer, and L2 equals 10 nanometer. Here, we're even closer to that. Actually, we're right on the boundary, just in by a 100th of a nanometer, or I'm sorry, a 10th of a nanometer. And that probability you should get to be really small. 7 times 10 to the minus 6. So basically non-existent, almost. So small. I'll underline these answers. Okay, so for D, we're given L1 equals, excuse me, we're given the right half of the box. So we're given, we can interpret that as 5 nanometer and L2 as 10 nanometer. And then when you plug this in, you should get P is about 0.5, which makes awesome sense because when we divide this down the middle into 2 halves, these shapes look similar, and half the time you're going to find it on one side. So I think it all comes back to the wave function. And then finally for E, we're given the central third of the box. So we can interpret that as L1 is 3.33 nanometer and L2 is 6.66 nanometer. And when you plug that in, you should get P is about 0.6. So going back here, I just wanted to say this is 50% of the time. And over here, it's 60% of the time, which, again, thinking about this shape makes sense. Because even though this interval is bigger, when you start in the middle and include the boundary, you're including more, I guess, of that area where that probability is less. But here, even though this boundary distance is a third of the whole thing, because it actually encompasses most of the area where the probability is the highest, 60% of the time, you're going to find it in there, which makes sense because this is what an n equals 1 wave function looks like for a particle in a 1D box. So when you consider this picture, all of these answers make very good sense.